now, section 5.2, definite integral. Okay. Here, the definite integral of f from a to b can be written in this way. Integral of a from b f of x dx, which is the same as this, which you have seen from the section 5.1. Okay. Okay. If this right-hand side limit exists, then we just write this right-hand limit as this notation, and say it's a definite integral of f from a to b. Okay. First note: definition is valid even if f has a finite number of removable or jump discontinuity, but not infinite discontinuity. So if we have a finite number of discontinuity, still we can define a definite integral. Note 2. If the symbol S, sum, this S integral, S is called the integral sign, and it was introduced by Leibniz. Here, this f of x is called the integrand, and a and b are called the limit of integration. With a is the lower limit, b is the upper limit. And x in dx is the variable of integrations. And integral a to b f of x dx is all one symbol. Okay. Integration is the process of calculating an integral. Note 3. The definite integral is a number. This is just a number. And it is independent of dummy variables x. So, even though we write it in this way, instead of x, if we use t or r, still, they are all same. The variable is a dummy variable. We can always replace it. And this sum is called the Riemann sum. German mathematician. And if f happens to be positive, then the Riemann sum can be interpreted as the sum of areas of approximating rectangles. Okay, let's see. And also this integral a to b f of x dx can be interpreted as the area under the curve f of x from a to b, like this. If it's a positive function, then that's the area, like this, from a to b. But if the function has a negative sign, then this integral actually means the area of these two with the subtraction of this area. Okay, like this. So this is actually net area. Okay, yeah, we can explain those in this website. So if we go to that website, then you see, and this shows what exactly what you have seen. And if we have a function minus 1/2 like this, then what we have is the area, the net area, this area, and subtract the bottom ones. That's the net area that we can see. Okay, so let's see example 1. Evaluate the Riemann sum for f of x is equal to 5, taking the sample point to be right endpoint, a is equal to 0 and b equals 3, and n is equal to 6. Then evaluate this. How? Okay, n is equal to 6, then delta x is equal to b minus a over n, so it's 1/2. And right endpoint is right hand. So 0.5, 1.0, and 1.5, etc. up to 6, 3.0. So Riemann sum R6 is like this. Okay? So R6 can be found as 28.75. Okay. So we can do the same, we can do it here, 5x here, 5x here, from where to where? From where to where? From what? From where? From 0 to 3 with 6, okay? From 0 to 6, 0 to 3 with how many? 6, 7, 6, like this. With the right hand. Then this is what we have, 0.489, and right approximation. Real integral value is about this, and error is very small, like this, at 8.3. Okay, this is what we can find. So the difference is 6.25. Okay, real integral with the Riemann sum. So if we make n bigger, then it will getting closer and closer to the real integrations. Okay, anyway, so if f take the both and positive and negative value in figure 3, then we have what dogu and okay, so then we have the negative. We have a negative area, so we should subtract the negative area from the upper positive areas to have a net area. So actually, this area is a net area from the positive side and subtract the negative side areas to have it. And what else to say more? So we need to deal with the Riemann sum to find the approximation. So it will be helpful to recall the formulas on the summation series. So we know all these rules well, which was covered in high school classes. So we use those rules to evaluate the Riemann sum of f of x is equal to 4 minus x squared with from 0 to 3 with n is equal to 6. Okay, and also we evaluate the integrals and compare the same thing. We just exactly same thing what we did to find the 0.625, and with n we find the intervals, and then follow those the integration with the definition of the Riemann sum. Then we have 3. So we have 3, and we have what 0.625. So the error exists. This is figure. This shows in figure 6. The area is 0.625 by this, by subtracting. So, So it's the same thing. So evaluate the x cube from -2 to 1. Do the same thing. Find the delta x and any point in the middle xi, and we do. This means this Riemann sum and limit of it. So we make the formula, and using the series summation of the series formula, we use it to get the solutions. Okay, which is this. So we have to do it by hand if we mistake it. So you save a lot of time by just code this formula to handle it instead of just substituting all the numbers and do the lots of summations of the series. We can always can draw the graph to find the rough approximation of it. Evaluate the following integral by interpreting each of the terms in the area. So find the area of this one. How we find it? So we this is a what? This is a 1/4 of a circle with radius 2. So instead of doing this computation, if we understand this nature from this given formula, then we can easily find the area of circle with radius 2 and just divide by 4 to get what you like to have. So it's very important to understand the nature of the problem. The integral is computed as area like this. And midpoint rule here. And here, this midpoint rule was shown here like what we did here. Midpoint rule for, this was x actually. This was x. Anyway, reload this once more and evaluate it. And then here, what we do is if we choose the midpoint, then we using the value in the middle of this each interval to have a height of this each of the rectangle, okay, to get the areas of each of this rectangle and just add them. That's the midpoint rule. So with this midpoint rule, if we, here, and this graph shows the area, okay, like this. And since we know from here, the area can be found divided by this rectangle and triangle and add it to get it. So there are many ways of it if you know the graph. Midpoint rule was explained, and use this midpoint rule with this 1 to 2, 1 over x squared. So we may just do it in here. What this is 1 over x squared. X squared, 1 over x, here, x to square here. From where to where? From where to where? Well, 0 to what? 1 to 2? From 1 to 2. Okay, here, with the midpoint rule, with n is equal to what? 3? 5? Okay, then midpoint rule, then we will have, we just try to reload it once more and evaluate it and give the function as 1 over x squared from 1 to 2, 1 to 2 with 5 and midpoint. Then we have 1 over x squared. That's right. We have the 0.5 and the midpoint approximation is 1.497, which is very close to 1/2. So yeah, like this midpoint. So you can deal with it, and you already knows the properties of the integration, definite integrals. Integral a to b to a, f of dx is minus integral a to b, f of x dx. If a is in the domain of f, then integral a to a, f of x dx is equal to already 0. And you can, for the constant, you have this. And for c, constant c can be factored out. And it's linear on plus and minus. Additive and subtractions are, the integral functions are linear on subtraction and additions. And all can be proved from the definition, like what you see. And so for this one, if c is the height, and from the interval from a to b is c times b minus a, so it can be easily verified. All others also can be easily verified from the definition of the Riemann sum. Evaluate from 0 to 1, 3 minus 2x dx, which is this. So you can use this. With the basic properties, you can easily find the answer. Okay? And the additive interval property. From a to c, f of x dx plus integral c to b, f of dx can be written as just 1 here. If it's a continuous function from integral from a to c and from c to b, then it's just used the same as just integrate the same function from a to b. So all are very clear. Comparison property of the integrals. If f of x is a non-negative function and a is always bigger, less than or equal to b, then it's the integrals are always positive because the positive function from positive integral, then it should be, area should be positive. You can easily draw the graph to figure it out. And if the function is always bigger than equal to M, little m, and less than equal to big M, then this area is in the big box, between big box and small box. So you can easily have these inequalities. Find the lower and upper bound for the integral. Then since this function is in here, so the area is always bigger than this one and less than 1 times the height of the square root 2. So so these are the things that you already know, the all knows, and here is the things that you can utilize. Here, you use just give any functions here and show the graph and find the integral and print it out. And if you want to find, then you will have for the integral, you will have these equations. If you want the exact value, then all you have to do is just a numerical approximation. If find the integral and print it and write it in a numerical notation, numerical approximation, then the point is the value is 0.422, something like this. I think that's it. This is the Lion King that my daughter recently drew and sent. Okay. Here's the problems on section 5.2, and I showed you the Riemann sum, the code, so you may use it to find the solution of this. You may use the code to give the solutions numerically. If you are familiar with it, then it will be enough, because you have done all of this work for the definite integrals during the high school years. Now, you just try what you haven't done it before. I think that that adds up. To find the area like this, you know the graph of this is half of the circle, so you can easily find it. And this is same as, you know the circle, and you know how this is a quarter of the circle, so you can find it. So if you can draw the graph, then there are many things that you can do easily. And this is a graph, so it's also of the showing these two different functions, and the area of it is, you can easily find this area times this triangle, subtract this triangle to get the answers, etc. So I think you are all ready to solve the problems in section 5.2. So team 2, I'm expecting they will solve section 5.2. Okay, is there any questions?